Okay, so maybe you'll see I'm trying to show a process, maybe I do, or I think anyone should do, where you draw complex pictures, simpler ones, and even the simplest ones. So I'm trying to get you to maybe like how you would even get to this classic turbo machinery picture. Maybe you don't need it, but these are things that I do to help me see like where on earth maybe these terms come from. So we drew the same impeller picture many times, and it had different dimensions. So let's focus on the radial. So all this stuff is about radial pumps. In your book, you'll see the exact same terminologies made, but for the windmills, compressors, etc. But you'll understand how to do it just from the centrifugal pumps or radial pumps. So that's what I got taught when I took the class, so that's what I'll do for you guys as well. So we drew the exact same one over and over again. The problem with the axial one is it had two dimensions we had to care about. Clearly the simplest one that we could make was this radial one where you just had a circle inside of a circle. It seems pretty easy to me. And then you had the situation, here's our coordinate system, right? Where you have some impeller design that maybe looks something like this. These are bad impellers, actually. Okay, so this is sort of what you want to categorize, and you know that there's some radial velocity, something spinning this. The torque you applied by plugging it into the wall is creating a torque to generate radial velocities. Okay, so these are the dimensions and geometries that we have to consider and care about. So maybe one of the worst things about this section is this god-awful like velocity triangle that is always put up there and is given to us to understand or something. But that's sort of what I'm trying to really draw these pictures about, to maybe help you understand the velocity triangle a little bit better. If it helps you, if it doesn't help you, you really can just ignore it because it ends up just being a velocity. But there are some benefits to maybe understanding this gosh darn velocity triangle. Some old guy's going to watch it on YouTube and scream at me, I bet. Okay, so the whole point is this thing is spinning, right? It's going at some radial velocity because I plugged it into the wall. And at the exact same time, I've shoved a bunch of fluid into the center of this thing from a pump coming out. And that fluid is also moving. So I have, even if it's just all piled up in there, regardless, this would actually still be spinning. So that's one velocity I have to keep track of. Now that velocity is really easy, right? And vectorially, you'll see where the vectors come from. I just know that I can calculate that, that power swing velocity just based on if I know this value, right? And it's just going to be the radial velocity times r. That's physics, sophomore year physics that you have. So that's my favorite one. I understand it the best. What else do we have to consider? Well, the other thing we have to consider is this fact that I had fluid go in, and now because it has to be pushed outward in the xy plane, it's going and it's swinging outward like that. So that's this idea of the W velocity, and which is just stated in words, which is sort of the fluid velocity relative to the blade. Okay, so that is the velocity that's really sort of on, right? That's right. If you were to just be sitting on the blade, right, that is where you'd see no slip occurring. So the way you think about that velocity is, in an ideal case, you'd have plug flow in, and then you'd have plug flow out, right? Sort of if you stopped all of the rotational motion and you just thought about fluid going in this way and then leaving that way, that would be what W is referring to, right? Think if I just turn the motor, if I just turn this off, right, and I just had something like this, and I shoved fluid right into this impeller, right? If I had enough force going through there, it would still pile up and then just move out based on what this is, based on this expansion, right? So you could see how, since there's some difference, right, in these areas, you get that flow rate relationship. But highlighting the fact that there is a reason that you probably should consider both of these velocities. Because at the same time as this process of this fluid going in, slowing down, spitting out of the impeller things, it's also spinning. So if we're going to write down equations, we have to come up with some contributions of both of these things. and figure out what the net part is. And that is what V is, right? So V is the absolute right? This is the quantity that we have to talk about, because if you only use this one or this one, you're clearly not describing the turbo machine. Because if I just use this one, the W, what I'd be describing is just shoving fluid into the center console and having it move outward if I just had the pump off. If I just use this quantity right here, right, you're just describing the motor function of the turbo machine. But it's this one right here that the quantities have to be described on, because it's that combination of how did my rotational energy, right, how did that affect the actual kinetic energy of the fluid? And that's what the U is going to be in there for. So, right, that is my little soapbox thing on maybe why on earth you would want to draw this thing. Maybe other people just totally get it. Okay, so then we have two scenarios for these impellers that we should think about, right? This idea of the fluid starting and the fluid at the very edge, right? So there's sort of maybe two of these things I would like to talk about. I'm going to look at this part and look at this part, right? So I have just look at the impeller blade. Like this. So there's one impeller blade I'll look at, right? Not enough room. So on this edge, right, you're going to have, let's say this is the W. So it's tangential to the impeller blade itself. Meaning, right, if you looked at all these curves, right, each of these would have its own W. So if you're at the very edge, right, you just draw that tangent out further. That's going to be the W. Now, what else do I have? I also have this radial velocity, right? That is W, right? And that's pretty, right, and that one, again, is a super easy one. Because if this is the radius of your impeller, right, which you can get from the diameter, maybe you knew that one as well, right? That one's nothing but just this R omega, right? And again, you just remember from you draw rotational motion in physics, right, that's just this radius times the angular velocity. So not that hard to calculate. And then you have this W, right, which is that, right, and the W is, right, the fluid motion relative to the flow, right? So, vectorially, right, that's where this comes from. So, vectorially, what we have to consider is the contributions of both these things, okay? And you can do the exact same thing here. I don't know if you'll be able to really see this here. I mean, it's in the notes, but again, I can do the exact same thing here on the interior, right? So on the interior, right, I also have a U, but it's a smaller radius, right? So clearly that term's going to be lower on the term here because, right, it's just R times W. Clearly this radius is smaller than that one, so I know this U is going to be smaller. And then I also have, similarly, just the tangential at the very part at the right. I have the tangential right there. These don't have to be the same, right? These W's, because they're tangential, right, they're going to talk about some angle, which we call beta in this world. So this is some W as well. And again, the summation. So, right, this allows you to kind of have this right, this a total V in and a total V out. Now I'll draw that single impeller blade. There's so many pictures, so many diagrams. Okay, so let's see if I'm just going to try and do this right. Boom. 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 Okay, so here, that's the impeller blade, right? This is tangential to the impeller blade itself, so here's my W. Right here is this U, that's the radial velocity that we have. And then right here is this V. Here, same thing, V2. Right here I have a U, W. These are kind of the geometric of importance. We can't. So this is beta 2. That's an angle. We could write that's some angle of a tangential to the impeller blade at the outlet. And then right here, it's beta 1. It's an angle for the interior, right? Think about there's going to be some sort of hub right there. So that's how I'm drawing this. So tangential, right? It should be this way, actually. Sorry. But that's the idea that you have some rub, it goes in, there's a W in, U in, it gives you a V in, and then you have a V2 out. So fundamentally, for a radial pump, right, the whole point is what? That. In a vector magnitude sense, you should remember what the magnitudes are. It's the sum of the squares. So even in three-dimensional, it's actually supposed to hold that you're right. What you're doing is you have to increase energy, right? The whole point is kinetic energy. Then you can just see that you would just do the scalar value gives the kinetic energy. The kinetic energy increases energy increases due to the work done by the blade. I use the work energy theorem all the time. It's the exact same stuff here, right? Right, and then sort of 3 is you have, right, biggest one, 3, is what? Housing. Housing is collecting the fluid, which is causing the pressure to go up because you're decelerating fluid to fill this volume, right? So those are sort of the physical things that we want and that we want to at least derive out of any equation we get for a turbo machine, just based on that simple picture.